Hiroyuki Mitsuya with Saginomiya, Japan. I'm very pleased to have this opportunity to speak to you today. The device shown here is the MEMS energy harvester we developed. We aim over 500 microwatts output from the environmental vibrations. We plan to put this in a commercial phase by 2022. My talk today is to show a method for optimizing the output power of MEMS vibrational energy harvester. We think that the energy source is the most important part of the IoT sensors because the conventional sensors need batteries that need frequent replacement, which is not practical for distributed applications. Ideally speaking, ambient energy is the best power source for distributed sensor networks. For instance, environmental vibrations, sunlight, heat, electromagnetic waves. Amongst of all, we have chosen environment vibrations as an energy source. It is in a middle scale in density, available in dark and night everywhere, and it goes through a hermetic seal, and therefore, our final goal is to replace a battery with a MEMS power pack, in which we have a vibrational energy harvester with a rectifier and a charge controller. Vibrations of 100 Hz and 0.1 Z are our final target to make 100 microwatts output. Small size of package is our priority, and hence we use mechanical resonance to enhance the output power from a small device because of the nature of the vibration source that we think of. We use a typical industrial vacuum pump as a power source for our energy harvester. The pump runs on power line and it gives mechanical vibrations. The figure on the right is an FFT analysis of such vibrations, where the distinguished frequencies are at 300s and 600s Hz, as commonly seen in most power line driven machines. However, these vibrations are too small to be directly used as a power source. Therefore, we used mechanical resonance of an energy harvester to get the power from small vibrations, which will be shown next. We made the structure symmetric to cancel the static force on left and right, and it could be shaken in a very small vibration range. These tiny fingers are all electrodes. We put a mass of tungsten to receive more kinetic energy. Suspensions are here on the four corners. The fabrication process for the harvester is this. We first use the standard MEMS micro machining techniques including photolithography and deep RIE. Then, after sacrificial release, we make the electrode. Finally, we put the mass onto the movable part. Here I will explain in more detail the solid ion electrode. Electrode is a dielectric material that keeps semi-permanent charges, which could be made by including potassium ions from KOH during thermal oxidation. We can make an electrode even on the thin walls of the comb fingers. The detailed mechanism is after oxidation with KOH, the potassium ions are bound with the oxygen atoms by the Coulomb force. But they could be displaced and expelled by the strong electric field at a high temperature, 600 degrees C. After which, we freeze them to leave the oxygen atoms negatively charged to make the electrodes. And this happens on the comb fingers. Then, for high energy recovery effectiveness, we need to eliminate the effect of the air damping. We used a ceramic package for vacuum seal. We set a metal lid on the package, and the size of the device was sealed by melting the metal in vacuum. As a result, the pressure in the package was 0.1 Pascal. And this internal mechanical loss can be almost eliminated. We learn simulation first by using the LTSpice for an equivalent circuit model, which predicts well the behaviors of MEMS harvester. The figure on the left is the stroke of the suspended mass when the load resistance is changed, where RZ is the impedance matched condition. It is quite notable that the peak oscillation changed more than a few tens of times by simply changing the resistance value. The figure on the right is the corresponding power output, which changes due to the resistance. And this one is experimentally confirmed. By using this test circuit, we used a differential amplifier to precisely monitor the output power. The resistance bridge here is to lower the voltage for the amplifier input. The picture here is an assembly of the test block, including an energy harvester. In a plastic box with two PCBs double stacked, shaken in this direction. Here are the experimental results when we vary the resistance. From 1 meg to 51 meg, the output changes as exactly as the simulation results and comes to the impedance matching condition here at 5 meg ohms. It also tells that the resonance shifts by 1 Hz. as the simulation results have predicted. We also checked the acceleration test as this. We set the excitation frequency at 299.9 and use two different resistances to plot the power as a function of the excitation acceleration. For the 4.8 meg, the max power is 1.1 milliwatt at acceleration around 7 meter per sec power. For the 10.1 meg, it was 750 microwatts at 4.5. Max power is good for 4.8 meg, but our target acceleration is around 3.5, and therefore we chose the 4.8 meg for the load resistance as it gives more power. This result tells us that we should choose an appropriate load resistance depending upon the excitation range. Let us then compare the frequency responses when we fix the excitation at 3.52. As we saw before, the 10.1 meg gives higher power at 300 Hz, and it was as high as 550 microwatts. On the other hand, the 4.8 meg gave a wide frequency bandwidth. From these results, we would say that tuning the load resistance is as important as making an effective mechanism for the harvester. In summary, we have developed a MEMS vibrational energy harvester for infrastructure's monitoring systems. The output power could be maximized by selecting the load resistance of the vibrational energy harvester according to the vibration conditions of a vacuum pump. We have achieved over 550 microwatts output power from real equipment vibrational characteristics. Thank you.